Dr. Nobin Paul, who is a postdoctoral researcher at the Korea Advanced Institute of Science and Technology, specializing in guidance, navigation, and control of aerospace vehicles. He holds a Ph.D. in aerospace engineering from IISc Bangalore, where his research focused on bio-inspired guidance strategies and variable speed interception techniques. His recent work introduces a nature-inspired guidance and collision avoidance strategy, drawing from the hunting behavior of hawks by analyzing real-world data on avian pursuit and evasive maneuvers. So now I invite Dr. Paul to deliver it.
Good afternoon, everyone. Thank you for the introductions. So, my topic is bio-inspired guidance and collisions avoidance strategy for advanced interceptor systems. So, I have referred one paper at the bottom. This is a work from University of Oxford and a Department of Biology. They conducted an experiment on Harris hawks, and they found out that Harris hawks attacks its prey using a mixed guidance law. That means it uses PN guidance law as well as the pure pursuit guidance law for the pursuit. So, based on that inspiration, I studied that work. So, I want to introduce what is Harris hawks initially. So, Harris hawks a major type of predators. So, it's major locations in Latin America and Western Europe. And they can hunt vertebrates larger than the hawk, and they have strong feet equipped with talons, and light wings help them for faster and quicker attacks. So this experimental setup is inspired from the work from University of Oxford. They uses an artificial foot lure for the target. They uses a set of pulleys to arrange in such a zigzag manner so that it can form a maneuvering and non-maneuvering phases simultaneously, and there is a perch location, so where from which the bird is starting its travel. So I have analyzed the data from those papers. So this work is inspired. This work I conducted during my PhD. So the sample trajectories, you can see the red one is the trajectory of the lure, and the blue one is the trajectory of the bird. And I have conducted the hawk analysis trajectory. These equations 1, 2 and 3 represents the position, velocity and acceleration of the bird and lure respectively, and equation 4 and 5 represents longitudinal acceleration and lateral accelerations. So the paper I referred before already discussed how the lateral acceleration of the bird and the lateral acceleration of the lure lateral acceleration lure and bird as how it is related. So actually, what is the lateral acceleration of the lure? So it means whenever there is a maneuver on the face, so the lateral acceleration increases. Similarly, whenever there is no lateral acceleration, it becomes zero. So my analysis in this discussion was, so first, what is the relationship between the lateral acceleration of the target in response? What is the target when and the longitudinal acceleration of the bird? Means when the target changes its position, how the speed of the bird changes. So I have conducted a analysis between what is the lateral acceleration of the lure versus the longitudinal acceleration of the bird. To the right side, you can see the figure, the relationship, how the bird's longitudinal acceleration varies in response to the longitudinal acceleration of the target. So I have calculated the correlation coefficient between the lateral acceleration and the bird's longitudinal accelerations. There was a negative correlation trend, means bird's longitudinal acceleration inversely responds to the lure's lateral acceleration. So further, I have plotted the scatter plots. It confirms that 98% of the flight data indicates negative correlation coefficient. Among these, 12% of flights have strong negative correlation, and 36% has moderate to strong negative correlations. So again, So again, I have come across the plot between the longitudinal acceleration of the bed and lateral acceleration with respect to time. There is a specific region where there is a more correlation, like more whenever there is a change whenever very closer to the target. So whenever the large change in the lateral acceleration is high and the response is very high in a particular location, that we can locate in some of the locations like this. So I have selected that region alone and again conducted the correlation coefficient analysis, and it has better results, like it is the correlation coefficient, negative correlation coefficient magnitude is greater than 0.9. So from this I analyzed all the characteristics and found out the relationship between the lateral acceleration of the lower versus the longitudinal acceleration, and there were 50 flight data from the paper. So I used all the data and analyzed, and the slope range is between range is between minus 0.8 to minus 2, sorry for that, and the combined mean slope was minus 0.85. So then from that I proposed a guidance law. So the guidance command consists of two acceleration, the lateral acceleration and the longitudinal acceleration. I have proposed that the lateral acceleration is given by the PN guidance law, and the longitudinal acceleration depends upon the lateral acceleration of the target. Here alpha t represents the lateral acceleration of the target. When alpha t dot equal to 0, the m launch is equal to mx, means the speed of the bird is increases, or the speed of the pursuer increases. When alpha t dot not is equal to 0, then at that instant the speed is reduces. This concept is introduced in the paper that we discussed, that is given at the bottom. So I have analyzed some of the cases like repeated circular target trajectory and rectangular target trajectory. So left side you can give the data, and the right side you can see the graphs. So from the graphs itself, it is clear that the control effort, means square of the lateral acceleration is lesser in the proposed guidance law than the PN guidance law. So this is for the results. So after that I have analyzed different mathematical analysis for the variable speed guidance law during my PhD. Then after I joined in KAIST for postdoc. So there I started working with collision avoidance, bio-inspired collision avoidance. So this is a brief literature survey. One of the team did the collision avoidance characteristics with the pigeons, and they have related it is proportional to the error angle between their flight directions. And the last paper, which is also similar to the similar work from the previous work that I have discussed, they model using a biased proportional navigation. So I referred that same paper, the same authors and same people from the University of Oxford. They conducted the same experiment in the presence of obstacles. So you can see on the left side, all the experimental setups are similar. Like there is a series of pulleys arranged in such a way that they can produce a maneuvering phases, and that they uses motors to move the loose artificial foot load, and they release the bird from the perch. So this is one video. You can see how the bird is moving in response to the both the target as well as the collision. So how they arrange that collision, arrange the obstacles in such a way that the lure can move through the gap, but birds cannot move through the gap. Like that they arrange. So from this inspiration, I have started working on this topic, how they relates. So these are the sample trajectories. There were 155 maybe flight data available. So I just selected 3 of them. And this is the mathematical analysis. So as I discussed, there is 8 obstacles in between, and Vm is the velocity of the pursuer, target, and O1 to O8 are the obstacles, and D1 to D8 are the distance between the pursuer and the obstacles, and gamma 1 to gamma 8 LOS angle to the obstacles. So the collision avoidance criteria and safe traversals through the gap, I have LOS angle to the obstacle should be multiple of 180, that's 0 or 180, and LOS distance to the obstacle should be greater than 0. So it's not like that bird always uses the collision avoidance strategies. So I have selected the collision concept, how they are implemented. So it is bounded by angle gamma n plus or minus delta n. So that is the angle you can see. So that represents the region of potential collision. So their biologically inspired safety margin for the bird is that radius is 0.6 meter, which includes the buffer distance, the hawk wingspan, and the obstacle structure, the radius of the obstacle structures. So from that I started working on what is the velocity profile. So as you can see, the velocity, the red one is the load velocity, is approximately, even though there is variation, so it's approximately constant, but the bird velocity has significant changes. So I plotted that acceleration profiles of the bird in the next graph. As you can in this set of the graphs, whenever the in this graph, that pink one represents that lateral acceleration and the longitudinal acceleration is the blue one, and the distance between the obstacles are given by the black curves. There are 8 objects. So whenever that distance to the obstacle reaches around 4 meters, so there is a significant change in both the lateral acceleration as well as the longitudinal acceleration. So that concept I have used. So I selected that particular region alone. So that is the bird's longitudinal acceleration and LOS distance versus time from the lowest distance, approximately 4 meter to safe gap traversal. That distance I have selected, and I have plotted the scattered plots. It has been seen that there is a positive correlation, which means that whenever the distance to the obstacle reduces and the acceleration is also reduces, means longitudinal, means the speed reduces when the target reaches to the obstacle. So I have calculated the correlation coefficient whenever the lowest distance less than 4 meters. So almost we got the correlation is positive correlation. Most of the cases it's more than 0.9, and we conducted a polynomial regression analysis to identify how the relationship happens. So I did the linear, quadratic, and cubic approximation. So now found that the cubic polynomial has mean error lesser mean error. So I selected a condition that bird's longitudinal acceleration changes with respect to the LOS distance in such a way that it follows a cubic polynomial. So I have I already discussed there were 155 data sets. I used all the data set to find out the A0, A1, the coefficients of the polynomials. So from that I have identified all the coefficients are settled at around mean, median, and mode around some particular value. So I selected mean of that, and I used those value for my upcoming discussions on how it is used for the aerospace vehicle. So this is the guidance and collision avoidance strategy that I have referred. So for this purpose, we have the 2 lateral acceleration, which uses the collision cone concept and the distance to the obstacle also, and I consider right now with reactive collision avoidance using PN, but we can use any type of reactive collision avoidance or any other types for this particular. And whenever there is a collision, chances of collision, it will move away from the target, and whenever there is no collision, it will follow the pursuit trajectory. So then longitudinal accelerations also contain the same thing that we discussed before for the guidance term. In addition to that, I introduced another term. It's a cubic polynomial, which relates the distance to the obstacle as well as the longitudinal acceleration, which helps to reduce the speed whenever that pursuer reaches nearer to the target. So I used that 2 types of similar trajectories, and I added maybe the obstacles in between, and the proposed guidance law. These are the simulation results. Main result is control effort is also reduced, And these are the some, and also I compared with the constant speed PN guidance with same obstacle avoidance, only the lateral acceleration control. So it has significant better results than the our proposed guidance law have better results than the constant speed plus PN. And this is for the rectangular trajectory, and these are the simulation results. And finally the conclusions. So we developed a biologically inspired guidance and collisions avoidance strategy based on the Hawk attack dynamics, implemented this concept in the advanced interceptor, and introduced a cubic polynomial based collision avoidance for rapid reactive obstacle evasion. Simulations show effective interception with robust obstacle avoidance in the cluttered environment. With this, I'm winding up my presentation. Thank you very much.
Thank you, Nobin. So we're open for questions. We have 15 minutes.
Hello, Paul. That
Yeah.
was a very informative session. See, actually, this Harris-Hawk optimization, there is a method, Harris-Hawk in optimization, that is. Any connection to that optimization method and what you are doing?
Yeah, I have seen some of the papers regarding the Harris-Hawk optimization, but that is entirely different from the concept. It is used in computer science for, I don't know exactly. Whenever I start reading that, it is not at all related to guidance or any of the parameter. I saw the papers related to Harris-Hawk optimization. There is no relation with my work. That is derived, I don't know how exactly, but it is different. I read some of the abstract about the Harris-Hawk optimization, but there is no relationship.
I'm just curious to know, so you got from photographs the trajectory you got it?
The data set shared in the paper itself, all the data sets.
No, but then how did they obtain? Like vision based, they just
Position
recorded
data.
position trajectory?
Yes.
Like vision based kind of thing.
They use the vision based method to collect the data set. From the collected data set, that they gave the XYZ position of the bed and blue. And in the obstacles also.
But in that one, I think you mentioned some more than 100, some big
150, yes,
150. So, but in that one, like outside, a lot of wind will be there, and these birds will take the advantage of the wind also.
For the first paper, they conducted it outside, but the second paper they conducted in a closed environment. So they haven't considered the wind, all other factors right now.
So in reality, this bird trying to capture it, the trajectory will be 3D.
Yes,
so what
yes.
you have taken is a 2D projection of that, and did it?
I will tell you. So there is, they consider in such a way that the perch, the location of the bird is as closer to the ground, so that they can easily convert into the two-dimensional. But the data set itself, they itself converted into 2D, like using, I forget the name, but it is a machine learning method. So they use the method to convert the three-dimensional data into two-dimensional data. That data is shared, not the 3D data.
Not the 3D data.
Yes.
Okay. Now why? So the vertical separation could be very less.
Very
also.
less, yeah.
Okay. So why I ask this is because if the vertical separation is not very less, right? If the bird is coming down fast, in the velocity, the forward velocity will still be the same, but in the projection, it will look as if it is decelerating.
Yes,
right?
yes.
So you're using that deceleration information and all, right?
Right now I'm not using, so I have considered the Hawk analysis they conducted, but the same concept they used for falcons. I have read those papers, but I haven't considered that. In future, maybe I will consider those also.
So in this, whatever data set you used, it's basically assuming that the vertical separation is,
Yes, yes.
the distance that the bird cover in vertical distance is not that much.
Yes, yes.
Okay. Thanks.
Hi Nobin, very nice talk, very exciting background to this guidance problem. I was just wondering, like nowadays we are talking about a lot of drone engagements, one-on-one, let's say quadrotor engagements, right? Neutralizing a rogue drone. So perhaps some of these ideas may be very useful there in those kind of engagements and 3D extensions also. Since you have the insight, I'm wondering if you have any comments on that.
Yes, I have gone through the applications, especially in some areas that not hawk exactly, eagles are used to catch the drones, rogue drones. So that is coming under that grasping mechanism. So 2-3 papers from EPFL, so I have shown those papers, how they designed a real drone, similar to the hawk attack. The same they refer the same papers, and they have proposed a new bio-inspired, but they mostly focus on the grasping mechanisms to catch.
So in the kinematic space, of course, if you have different constraints, let's say there are 2 different types of quadrotors, so their kinematics will have different constraints. So this may be, your analysis is beautiful. So I believe, I mean, just as a comment, maybe you can look into that.
We will try. I will try to do the practical applications.
Yeah,
so I already implemented that LAVS guide, this particular guidance law in drones. Let's see.
Okay, wonderful. Thank you.
Thank you, Nobin. Very nice talk. In the second part of the study, you have both collision avoidance as well as pursuit of the target, right?
Yes, sir.
So, is it possible to decouple the action of the hawk for collision avoidance and for chasing the target? So,
right now, what I did, I decoupled it. So whenever it reaches nearer to the obstacle, for example, that paper itself, it is near to 4 meters. What I did is, it reaches around 25 meters. It will decouple from the longitudinal, maybe that from the guidance concept, and we will use the obstacle avoidance consideration. So right now I have implemented the system in a decoupled manner. Okay. Whenever we uses in a coupled manner, what I faced, so if with the longitudinal acceleration, that lateral acceleration because of the pursuit behavior, that if it is higher than that obstacle, there is a chance. If our lateral acceleration is restricted, there is a chance of the obstacle collision. So in order to avoid that, right now I have decoupled it for a very closer to the obstacles.
Yeah, but in reality they are not decoupled.
In reality, so even the video is also, we can see that it is still following the trajectory, maybe the target. Yeah.
So is it possible to assess what is the effect of whether the hawk is able to predict the motion of the target and accordingly change its strategy? Is it possible to get that information? Because you have so many data points, right? 155 flights are there.
Okay.
So maybe that is something you could look at.
That I need to look clearly with the data set. So how it is. For practical implementation, I decoupled, but for that analysis, anyway, it is related. Both are related. Both are used for this bio-inspired thing.
Thank you, Nobin.
Hello. Thank you so much for this amazing session. I just wanted to ask that, as it is inspired from the hawk attack dynamics, so are there any other applications as well we can use this, we can use this guidance in any other fields as well?
Right now we can use it for the drones.
Okay.
For the missiles, there is a practical difficulties with changing the speed, but there are a new concepts. Speed changing missiles are there, but still there is some practical difficulties. So right now we can easily implement in drones, because drones can reduce the speed, increase the speed so quickly using easy control method. So we can implement this concept in drone. Even more ground vehicles also, robots also we can use.
So basically we can use in navigation as well, right?
Navigation of what? Right now?
Navigation direction.
We are using collision. We are using that navigation concept, guidance law, and that trajectories. We are using. For example, if we have some waypoints between these two, we can use.
Thank you.
Yeah.
Hello, Dr. Nobin. That's a very nice piece of work. So I have series of questions, sort of. So is the assumption is that in all the 150 plus trials, the body is assuming the same strategy? And if not, how can from the data can you study whether there are multiple strategies adopted by the bird in different cases?
So what I can suggest, so what I have used the entire data set here for the statistical analysis. Yeah, you are right. I have gone through the different. In some cases, is entirely different, but majority of the cases they uses this strategy. It is not like that. In some cases, they even didn't. They even reaches that target before the obstacle. So those cases we cannot do anything, right? So, but majority of the cases they uses this particular concept. Whenever it reaches nearer to the target, nearer to the obstacle, the speed reduces, and correspondingly the angle is also changes. The concept is using there.
Okay, thank you. And follow-up question is, it's sort of a follow-up from one of the previous audience members' question is that, suppose there is wind, from case to case there will be different disturbances, there might be noise in the measurement, there might be a difference in strategies from one bird to another, there might be many sources of uncertainty. So will that be reflected in a grave manner in the data you see, and if they're present, how can one take care of such variabilities?
So all the wing disturbance or other disturbances are belongs to the pursuer and its capacity, right? So for birds, they smaller wings or winds or everything, they will try to maintain this wind disturbance as its own, because they have its high capacity for the thrust, maybe that variation, all those things. That is my one assumption. I don't know, but because they haven't
I'm
conducted.
just asking from your point of view, from the guidance person's point of view, that he doesn't know what the bird itself doesn't know. It just follows his instinct and captures the thing. When we are analyzing, we take into account the different effects of winds and all. So, in your scheme of things, can the disturbances be accounted from case to case? That's one of my queries.
Right now, in this analysis, I haven't considered the wind disturbances. So if wind disturbance is coming, so we need to, I need to analyze again how it affects the guidance laws or guidance strategies. So basically, whatever the situations, if wind is coming, the bird need to take some strategies to nullify those effects, and it focuses only on the target and the obstacles.
Okay, thanks.
Thank you for the nice presentation. So I have a little doubt. So you talked that this experimental setup is kind of a constraint setup. So I am wondering how different it could be when it is in the open environment, and how different the maneuvers of the hawk will be as compared to what they have found out from the data set.
Yeah, it is serious suggestions. So I haven't looked those external constraints right now for my analysis. So how they are affecting, we need to identify for the particular hawk. For time being, they are able to overcome those effects. That is one thing. And for us, we need to think how that wind affects all other things, how it is affecting our guidance law, and we need to model according to that. Right now, I haven't considered the external effects on this guidance law and this analysis.
Thank you.
Hi sir, it was a very good presentation. I had a simple question, was that if the path which the hawks are taking, is it an optimal path directly? Like the path which they take and an optimal path, are they the same? Or is there any particular difference between the path which they take from the optimal path?
So optimal path, basically mostly that hawk is always pointing towards the hawk. So the target. So why they need to reduce the speed such that if it is follows the speed or maybe particular target, it need to take more paths to attack. But so birds is try to reduce and increase the speed for this optimization, speed optimization also, and the path optimization. But we are not sure how optimization, what optimization, all those things we are not sure. But this variation in the speed and this angle changes, they use for this particular thing, right? That is the reason why the control effort is lesser with the variable speed guidance law compared to the constant speed.
Yes, sir. So, based on the flight data which was collected, I think 150 flights approximately, would there be a difference when there's another bird, same species? Will there be a change in the strategy applied by the bird to catch the lure?
So basically hawk, so another bird, the question is if there are two birds, is it some game kind of thing you are telling or?
No, sir. It's like if you take two birds of the same species,
Okay.
would there be a difference in the strategy applied by the birds to catch the lure? Like two birds at the same time, if they're released, there's a particular single lure of a kind. Is there going to be a difference in the way the birds are going to think and apply their strategy to catch the lure?
Yeah, definitely there is difference, because when I analyzed the first paper, there is 50 flights. They use 5 birds. So in all the cases that correlation coefficient is not exactly same, and that relationship is also not same. Some of the birds has more more of kind of that relation, that constant, maybe linear relation constant, and but some of the bed has lesser values. That is, it is because of the different beds strategies. Even though they have the different variations, that is only related to the magnitude, not exactly the concept.
Okay, sir. Thank you.
Someone will go more faster, lesser faster, like that.
So yeah. Thank you, Dr. Nobin.